Exercise 6.26. Prove that for every n greater than or equal to 2, neither the line nor the circle is homeomorphic to Sn. Okay, well, let's deal with the line first. So assume for contradiction that the line is homeomorphic to Sn, and so we have a homeomorphism f from R to Sn with n greater than or equal to 2, and well, we're going to proceed just like we did for Rn in the previous problem. So the origin is a cut set of R, and so its image under this homeomorphism, the set consisting just of f of 0, is a cut set of Sn. Okay. So the complement of that point in Sn is disconnected. All right. Well, that's just not true, right? We can show that the complement of this point f of 0 in Sn is connected because the sort of punctured n-dimensional sphere is homeomorphic to Rn by what's called stereographic projection. In the case of S2 here and R2, you basically sort of pull apart the sphere at the North Pole here and send these points close to the North Pole off to infinity in every direction, and you get a plane. Okay, and it works. The same idea works in higher dimensional cases as well. Okay, so Sn minus this point is homeomorphic to Rn, which is certainly connected. Therefore, this punctured sphere is connected as well, contradicting our result from up here. Okay, so sure enough, the line is not the same thing as a sphere in dimension 2 or higher. Okay, well, what about S1, the circle? Is that the same space? Is that homeomorphic to a unit sphere in a higher dimension? Okay, well, it's not. Let's assume it is for contradiction. So we have a homeomorphism G from S1 to Sn. And, okay, we're still using connectedness to distinguish these things. And we can't do just one point like we did for the real line. We need 2 points to disconnect a unit circle. Okay, so if you take our favorite 2 points, 1, 0, and 0, 1, in S1, they do form a cut set for S1. And then if you look at the image of these points under this alleged homeomorphism G, then you get 2 points in Sn. Right? We'll call that set of 2 points A, and it has to be a cut set for Sn. Okay, and it's important to note that we do actually get 2 distinct points, right? In general, maybe these 2 points would map to the same point, but that can't happen because G is a homeomorphism, and so in particular it's a bijection. So in particular it's injective. All right, so if A is a cut set for the sphere, that means that the complement of A in the sphere is disconnected. And another way of saying that is if you start off with sort of a punctured sphere where you're missing one of those 2 points, then the other point, the set consisting just of the other point, is a cut set for that space, right? Because if you take that space and take away this point, you have the same thing you had up here, Sn minus A, so it's disconnected. All right. So how are we going to get a contradiction from that? Well, this punctured sphere, as we noted above, is homeomorphic to Rn, okay, by stereographic projection. And so if you take the image under this homeomorphism, which I'll call H, of the second point G of 0, 1 of this cut set, then you get just this set consisting of this single point, H of G of 0, 1, and that's a cut set for Rn. Okay. But as we've shown above, Rn minus a single point is connected. So that single point cannot be a cut set.